Everyone, my name is Jihan Ma, and I'm a PhD student in biomedical informatics at UNMC. Today, I'll be discussing an NP complete problem, the clique problem. And specifically, I will delve into what it is, its approximation, and algorithms and computational challenges. Here's an overview of my presentation. I'll begin with an introduction to clique problem, detailing its definition and why it is classified as NP-complete problem. Next, I will highlight its real-world application to demonstrate its practical relevance. I will then explore approximation algorithms, particularly focus on meta-heuristic approaches. Following this, I will discuss quantum algorithms, including their potential advantages and challenges. Finally, I will wrap up with the key takeaways from the discussion. Okay, what is clique? A clique is a subset of vertices in a graph where an edge directly connects every two vertices. So as you can see in the graph, first of all, you can see the clique of 3. In the first circle, there's a 3 dot connected with each other. And in the second circle, there's the clique of size 2. And continuously, and then you can see the clique of size 4. And below you can easily find this clique of size 3. And in the right graph, you can easily identify that this maximum clique, it's 7, k equals 7, which is, you can see that in the blue dots are connected with each other. The clique problem can be framed in several ways depending on the type of questions we are asking. It involves all 3 types of algorithm problems: the decision problem, which asks us whether a graph contains a clique of size k; the optimization problem, which asks for what is the size of the largest clique in a graph; and the search problem, which asks to find all vertices that form a clique of size k in the graph. In this presentation, I'll primarily focus on the optimization problem, which is NP-complete and NP-hard problem. The clique problem is both NP-complete and NP-hard, making it a central challenge in computational theory. But what does this mean? As shown in the diagram in the left, NP-complete problem belongs to the intersection of the 2 categories. NP, the problems whose solution can be verified in the polynomial time, and NP-hard problems, as hard as the hardest in NP. The clique problem, as one of the 21 NP-complete problems, exemplifies this computational complexity, illustrating why finding a efficient algorithm for such problem is exceptionally difficult. As you can see in the diagram, a problem is the NP-complete if its solution can be verified in polynomial time, which is NP, and if all other NP problems can be reduced to it. The clique problem falls into this NP-complete category because verifying whether a subset of vertices forms a clique is straightforward, but finding the maximum clique involves exploring all possible subsets, a process that grows exponentially with the graph size. Clique problem has diverse real-world applications. First, maximum clique problem is utilized to identify the largest group of friends or communities within a network. This helps in studying phenomena like rumor spreading or stopping, and then epidemic modeling and opinion dynamics, and so on. The cliques are used to detect highly knit community or subgroups within a network, as illustrated in the first graph. And also in computational biology, it helps in identifying protein-protein interaction network, where a clique represents a group of proteins that interact with each other, forming critical functional modules as shown in the second graph, which is similar to the social network analysis. And cliques are also used to group comparable tasks or allocate resources efficiently, ensuring optimal operation in logistics and task management. Lastly, cliques also can be used to represent a subset of code words that share specific relationships, aiding in error detection and correction, which is critical for data transmission and storage. There are some historical algorithms and approximation used to solve the clique problem. The first is the brute force algorithm. This method involves enumerating all subsets of vertices in the graph, checking if each subset forms a clique, and then returning the largest clique found. Where this guarantees an accurate result, it is highly computationally expensive, with a complexity of O of 2 to the power of n times n squared. Another one is a greedy search algorithm, which is the simpler, faster approach, but it does not guarantee finding the largest clique. It starts with an empty clique and iteratively adds the vertex with the most connections to the current clique. The complexity of the algorithm is of n squared, which is much more efficient for the larger graphs. Lastly, the branch and bound algorithm. This method systematically explores a subset of the vertices, but employs pruning to eliminate subsets that cannot form larger cliques, which is significantly reducing the computational burden. So it is faster than brute force in practical scenarios, especially for the graphs with specific properties. Its complexity is approximately of k times 2 to the n over 2 power. In this slide, we can explore the meta heuristics for clique problem. Meta heuristics are powerful optimization technique aims at finding approximate solutions for NP-hard problem like the clique problem, which is finding exact solution is not feasible. One popular meta-heuristic approach is simulated annealing. This method is inspired by the annealing process in metrology, where materials are heated and slowly cooled down to reduce their defects. For solving the clique problem, this method interactively explores a subset of vertices in a graph and evaluates their energy, which corresponds to the size of the clique. A key feature of this method is a probabilistic acceptance of worst solution during the process, allowing it to escape local optima. As the algorithm processes and the temperature decreases, the focus shifts toward refining the solution to coverage closer to the optima. From this graph, you can see that we can find this is a local minimum as local optima. So, and then also in this meta-heuristic method, especially this simulated annealing method, utilizes the energy function of E of C equal minus absolute value of C. So in other kind of NP complete problems utilize this simulated annealing methods. They may have a different energy function, but Clique problem has utilized the energy function of this. The other meta-heuristic method, there is a kinetic algorithms, which involves a population of this solution by simulating natural processes such as selection, crossover, and mutation. It is particularly effective for discovering cliques in large graphs with complex constraints, offering flexibility in diverse scenarios. Another one is ant colony optimization, which mimics the behavior of ants finding paths to find food, using pheromone trails to guide the search for cliques. This method is particularly useful for graphs with many local optima, as it facilitates a robust exploration of the search space. And lastly, particle swamp optimization simulate the movement of particles in the search space, where particles adjust their positions based on individual and group best positions. So this all approach adapts effectively to dynamic graphs, offering a promising method for complex and evolving problems. In this slide, I want to introduce quantum approximate optimization algorithm as a quantum approximation. There's no polynomial time quantum algorithm for the Clique problem, but this QAOA is a quantum classical hybrid algorithm designed for optimization problem, especially for the maximum Clique problem. In this method, the key principles are Hamiltonian encoding and variational optimization. The solution to the MCP is encoded into the group state of Hamiltonian, which is essential the energy function of the quantum system, and parameters gamma and beta are optimized to approximate the ground state of this Hamiltonian, which will be guiding the quantum system toward the optimal solution. The quantum approximate optimization algorithm offers a digital alternative to quantum annealing with a tunable precision, which makes it versatile for optimization tasks. It has shown promising results for specific graph classes such as unit disk graphs and King's graphs, with tests involving up to 80 vertices. On the other hand, this method requires the integration of the classical optimization techniques to refine the variational parameters like gamma and beta, and this adds the computational complexity. So also scalability is a kind of challenge because some limitation in the size and noise level of the current quantum hardware. That's my conclusion. So Clique problem is a fundamental NP complete and NP hard problem in which no polynomial algorithm efficiently solves the problem. And Clique problem is widely applicable in various fields, including social network analysis, bioinformatics, and scheduling and coding theory. Classical algorithms such as brute force and greedy search and branch and bound offer solutions, but are often computationally expensive. Meta heuristics are well suited for the practical and large-scale problems with heuristic solutions. And similarly, quantum algorithms like the QAOA holds promise for achieving speedups and on constrained graph types, but are limited by current hardware advancement. So more advancements in quantum hardware and hybrid algorithms could bridge the gap between the theoretical and practical scalability. This is the references of my presentation. That is all for my research on the Clique problem. Thank you.